Let's get started. Good afternoon. Thanks for coming to this talk. My name is Yong Tang. I'm a maintainer and the CGI lead for TensorFlow project. My co-speaker, Yuan, he's a member of KubeCloud and approver and reviewer of KubeClow's mpi-operator. He's also a maintainer of several open source projects as well. Unfortunately, Yuan is not able to attend this talk because of the schedule conflict, so I'm going to cover his part as well. In today's talk, I'm going to discuss about large-scale distributed deep learning on Kubernetes clusters. I'm going to briefly discuss about TensorFlow, discuss about Kubernetes operators, and also discuss about KubeFlow, which is the main focus of this talk, because the operator we talk about, the TF operator, PyTorch operator, and MPI-operator all belong to KubeFlow org. So let's get started. So before we jump into the deep learning orchestration, I want to briefly discuss about the background of TensorFlow. As many of you already know, TensorFlow is one of the most popular open source frameworks for machine learning. It was originally developed by Google. It has been open source since 2015. Since then, TensorFlow has seen quite explosive growth both in open source and the machine learning community. At the moment, the most stable version of TensorFlow is 1.14, which was released several days ago. But the TensorFlow 2.0 is actually up and coming and will be released soon. I want to discuss about some of the changes in TensorFlow 2.0 because a lot of things has changed, and that's actually quite an impact to many areas we'll discuss in this talk. In TensorFlow 2.0, the biggest change is obviously the eager execution. Back in TensorFlow 1.x, the static graph was executed, which means if you are going to run a program, instead of running it in an imperative way, you have to construct your graph and wait for the graph to be deployed, and once it's finished, you get the result. This is obviously very good for production deployment, but it also has a disadvantage in that if you try to debug, it's very hard to debug because you will not get the result immediately. So in TensorFlow 2.0, the biggest change with the execution model is that eager execution has been enabled. You can just run TensorFlow like just like a Python program very natively. Another big change in TensorFlow 2.0 is that Keras essentially is recommended high-level API, and all other model building APIs are pretty much dropped. In TensorFlow 1.x, people have seen criticized 1.x in that for high-level model building, you have several different ways. You can use TF estimator, you can use TF Keras, you can use TF layers, you also have the TF sleeve. There are 4 different ways to build models. In TensorFlow 2.0, the decision was that TF Keras will be the recommended API, and moving forward, all other methods will be deprecated pretty soon. If you look into the TensorFlow 2.0's workflow, you can notice that everything starts with data input and pre-processing, which is handled by TF data. TF data is a pipeline to take the data from other sources and import that into TensorFlow's graph. This is one of the most important steps, and this will be one of the focus of this talk because the data processing is very much tied to the orchestration of the deep learning. The second step, after the data has been imported into TensorFlow's graph, is a model building. Obviously, we talk about TF Keras and TF estimator, although TF Keras is a recommended way. for training, now you have the eager execution. Also, you could use the TF function to predefine a small graph so that the execution can be speed up. And finally, for saving training and inference, you could use save the model to save the model you build and reload back. So that's TensorFlow 2.0 workflow. If you look into that, you'll notice that data input, preprocess, and model building probably are the steps that's going to be needed before you do the training. So people always ask questions, say, okay, what's so special about data input, model building, and how to apply that when you have a big cluster? So let's come up with the topic of orchestration for deep learning. When we talk about orchestration, we actually talk in deep learning, it has a very special meaning. Most importantly, orchestration for deep learning is always tied to the GPU. We all know if you want to run a deep learning task, you're going to deal with I/O, which could be input/output. Most likely it's going to be network input because the data will be loaded from disk to memory pretty easily. Then the second piece is a CPU. CPU is pretty much still needed for deep learning because not all the operations are feasible for GPU. There are some operations just naturally not a good fit for GPU, so you still need a CPU for certain operations. And also, CPU is typically the way to interact with I/O. And finally, you have a GPU. That's a heavy lifting piece to be done. But if you look into that, the biggest problem is that GPU is the most expensive one. And inappropriately, if you're going to run your orchestration, you'll notice that if the deep learning is not scheduled very nicely, you are going to waste a lot of GPU. And that's a big waste for your investment. If you look into the diagram shown in the slide, on the top, you could see that you do a batch processing. You take the data from the input. It passes through CPU for pre-processing. The next step is pass through GPU for training and inference. As you can see, until data has reached to a GPU, your GPU is going to be idle and you waste a lot of resource. On the bottom, that's the optimization of your orchestration and the scheduling. In this case, you try to build an I/O pipeline such that the data will be delivered to GPU as soon as possible. And once it's in GPU, most of the time you can do the training and do the I/O in parallel such that you fully utilize your GPU. And that's the efficiency we talk about for orchestration. There are several different ways for deep learning orchestration. The most common way is the so-called pyramid server model, and for TensorFlow, that's probably that has been in place for since almost the beginning. The parameter server model essentially defines a parameter server, which could be a subset of servers that's dedicated for saving parameters. You also have workload, which is GPU heavy. The workflow for parameter server model is that for each workload, it's going to collect a subset of data and it's going to calculate the gradient. The partial gradient will be passed to the parameter server. When parameter server collects all the gradient, it will do the calculation, gets the weight, and the weight will be further feeded back into the workload to do the update. This process will continue. Parameter server, like I mentioned, has been pretty much in place for quite several years, and people invest a lot of money, invest a lot of resource to improve that. But there is some debating about whether parameter server is the best way to handle deep learning orchestration. The biggest concern is that there are some discussion about Prometheus server Prometheus server model probably best fitted for scenarios where you have your compute power all seated on the same machine, so that your memory are shared by different GPUs. But in case of distributed deep learning, your GPUs are actually scattered around. They could be on different hosts, and they have to talk to a Prometheus server. When they talk to a Prometheus server, they have to go through network transfer, and there are huge amount of data are transferred back and forth between Prometheus server and the worker node. That could be a really big burden to your training. But anyway, in the old days in TensorFlow, Prometheus server is pretty much the only potential model you can run for distributed deep learning. Recently, people have been talking about if we can use some other ways to do the distributed deep learning. Most people actually resort to the MPI model. In MPI, distributed parallel processing has been resolved in a way for a long time, and there are several ways to do in MPI to do the calculation. In MPI, there are several models for reduce operation. One is the reduce, another is the AllReduce. So I'm going to show an example of the reduce. So what is the reduce? Reduce, if you look into a graph, that's going to show you exactly how the reduce is essentially just for each node. You are going to do the calculation, and if you look into this graph, you try to do a summation. When you do the summation, you start with the bottom node, you do the calculation, do the summation, and at each node, you're going to sum up. And for each step, you do a reduce once until you reach the root node. So if you show it that interactively, it's going to be like that. So the final step is that you reach to the root node, which is the summation of all your node. That's 28. Let's reduce. MPI also have another of so-called AllReduce. So what is AllReduce? The AllReduce it's essentially the same as the reduce, except when the summation has been calculated, reach to the root node, instead of just stop here, you're going back and broadcast back to every node. So every node knows your result. So if you're looking this way, you try to do the summation. You start with the bottom node, 1 and 2, that's 3, and the plus 5, that's 8. You do another summation, that's another node update. And another summation, you reach the root node. Once you reach the root node, the result 28 will be broadcasted to every node. So it's going to be like that. So that's a so-called AllReduce. So to sum up, the AllReduce is a reduce plus broadcast, and for many people familiar with MPI, they believe that's a more efficient way of doing distributed calculations. So let's go back to revisit Prometheus server, because like I said, in TensorFlow for a long time, Prometheus server model is a standard way of doing distributed deep learning. The debating is about parallelize on a machine and parallelize in a cluster might be different things. Many people believe that Prometheus server model is only suitable for parallelize on a machine. It's not suitable to parallelize tasks in a cluster, and it's kind of controversy. The biggest burden for Prometheus server is that the cross-device communication cost is very high. But unfortunately, a huge effort has been invested over the years, so you probably can only take that. I spend a lot of time discuss about Prometheus server, mostly because if you talk about all the existing machine learning authorization frameworks, they actually have the assumption that they use Prometheus server, and that's not necessarily the best approach. So that's kind of like making the decision of choosing the best so-called deep learning for deep learning authorization frameworks kind of difficult, because whatever framework you try to choose, it may not exactly fit the scenario you want to achieve, because in this field, a lot of things are changing very frequently. So many of the frameworks, if you, for example, if you use some framework, you probably notice that they cannot even run with new version of TensorFlow. So that's going to be a big issue. Anyway, if we look into the authorization for deep learning, we notice there are several things. If we summarize the past diagram, we mentioned about the Prometheus server model, about the reduce and AllReduce model. They all require stateful metadata, and they also require life cycle management, which come up to the situation where we feel like we probably can use Kubernetes for authorization. And also, when we talk about our Kubernetes, we also think it probably makes sense to have Kubernetes operators for machine learning as well, because it's just a natural fit to manage stateful data and to manage the life cycle. So let's go to Kubernetes operators. In this talk, I'm going to just briefly cover several operators and needs KubeCloud organization, the TF operator, PyTorch operator, and MPI-operators. PyTorch is it probably has a focus on PyTorch, which may have some competition with TensorFlow, but I want to cover this part as well. A TF operator, that's obviously it's tied to TensorFlow. It supports TensorFlow. It also supports TensorFlow TF distribute strategy. So this one has is slightly better in that TF distribute is relatively new, and TF distribute it's actually support a different strategies and the backend like MPI, NCCO, Prometheus server, and TPO model. The TPO is the chipset, the chip designed by Google. That's a tensor processor unit. PyTorch operator has a focus on torch distribute module. It also has support for MPI and NCCO. Hovorod, that's developed by Uber. Hovorod actually has a wider support for different frameworks, but I want to point out that some of the distribution strategies are probably not exactly fit for a newer version of TensorFlow. But anyway, we'll just show those TF operators and MPI operators to be deployed on KubeCloud. So as you could see, they are pretty much very similar. The difference is that so first of all, you have a different kind of job. There's a TFJob and the MPIJob. The spec is either TF replica spec or MPI replica spec. The command line is slightly different, but other than that, it's pretty much the same. So the container image are the same. So let's look at the if you have a TensorFlow. Let's start with TensorFlow program. So how do we run a TensorFlow program? You install TensorFlow, and you can also install TensorFlow IO, which give you the TF dataset support. So the first line, of course, is to load the data into data set. That's the first line of what data set equals the MNIST data set. The data set will do some transformation, which is necessary because you need to do some pre-processing so that your data set is in flow 32 data types. You also do a batch of 1000 because batch is a way to help you for your data to fit into a GPU in one process. If you pass the data one by one, it may not be very efficient because the data transfer from CPU or from memory to GPU is also very expensive. So next is the model building. As we mentioned now in TensorFlow 2.0, everything has been consolidated into carriers. So you try to build a model that's going to be a sequential model. The first layer is a flatten, and then you come up with a dense layer. Dense layer is standard layer. The next layer is a dropout. Dropout is a technique to prevent the overfitting. Essentially, if you define a dropout with in this model, you have a dropout with a rate of 20%. That essentially means during each phase of the training, for every node, the chance this node will be dropped, and this chance is 20%. This will help prevent the overfitting problem you normally encounter when you build a new network. The last layer is a dense layer as well. So as we can see in TensorFlow 2.0, everything has been simplified. So if you build a model, the next step is to compile the model. That's one line. And after that, it's a model.fit, essentially give you the training. The data set has been passed in. The last line, as you can see, that's evaluate. That's actually the inference phase. You can do that, or you can optionally skip this step if you're only focusing on training. So this program we are talking about just build a model and run it on TensorFlow. Now we talk about distribution. Of course, that's the focus of this talk. So how do we do distributed training? So there are several strategies. One strategy in TensorFlow now has a mirror strategy. It's actually consolidated a lot with mirror strategy. All you need to do is just define a scope of with mirrored strategy.scope, and the model compile can be done automatically, which seems to be nice, right? We talk about the mirror strategy. We also want to mention that in the old days, you have when you do distributed training, you have other tools available that can help you. For example, like Hovorod. If you combine TensorFlow with Hovorod, it's pretty much similar, except that you have to pass different options and use callbacks to achieve the result. One thing I want to point out is in this example you have TFtrain, but TFtrain has been deprecated in TensorFlow 2.0 as well, so it's kind of unfortunately. Like I said, there are a lot of things in TensorFlow 2.0, so which actually makes things a little bit messy. But that's also a good thing because it actually give you a brief idea of how fast this area is moving forward every day. Like we talk about 1.0, just like how long time ago, like 1 or 2 years ago, and all of a sudden we jump into 2.0. A lot of things change, like a parameter server model, like the TFtrain has been replaced, deprecated. Even TF estimator, which used to be the default way of building a model for many programs, now all has been gone in 2.0. Let's do a comparison. But anyway, let's do a comparison. So as you can see in TensorFlow 2.0 versus Hovorod, they're pretty much the same. You build a similar model. When you do the distribution, because it's in Python, so a lot of details has been abstracted and hidden. So you could see it's trying to make your life easier. We also try to cover a little bit of PyTorch plus Hovorod. Because Hovorod, one thing with Hovorod is that even if it's not exactly a fit for TensorFlow 2.0, it still has some usage with MPI and with PyTorch. So you can see they behave slightly differently, but they are pretty much similar as well. So that's one of the positive side of different of a framework that can support different open source softwares. Let's just go back to TF-operator versus MPI-operator. They are pretty much very similar as well. As you can see, they abstract all the details. So now you can see even the YAML specification for your Kubernetes for running your Kubernetes operators are very much similar, except for the last command line that's slightly different. So as we discussed, this field is too fast in moving forward. Every day, a lot of things change. I mean, if you try to install, for example, TensorFlow, and you try to install nightly, and you probably notice that whatever you're trying to run may not work after like a month. And within several months, TensorFlow 2.0 will be released, and there will be further change. So it's really hard to conclude what's the best solution for you to select at the moment, because whatever that is, you have to make sure your authorization framework can support the best software with the latest version that's stable, right? So what's the conclusion coming up with to this stage? The conclusion is that if you want to focus on deep learning authorization, first of all, you have to focus on trying to fully utilize your GPU, because that's the essential piece. Otherwise, deep learning authorization is probably not worth a lot of effort to waste time on that. Another piece is if you try to people tend to debating about if you want to find a framework that's going to support our platform or our frameworks, or you want to find a framework that's going to dedicate for something. It's really hard to say. Like I said, initially TensorFlow only have a parameter server for distributed TensorFlow, and later on we have the mirror strategy. We also have like AllReduce strategy introduced in TensorFlow TF distribute. That actually simplify a lot of things. I think that's something you want to take into consideration when you try to come up with a solution that's going to build for so-called AI ops or so-called machine learning on Kubernetes, because whatever you're trying to build, it may not be feasible after maybe just several months. I see a lot of people just smiling, just think, okay, what exactly are you trying to deliver? Unfortunately, I think that's a status quo for the current state of distributed machine learning field. It's too tied to a distributed framework, and it's probably hard to come up with a stable solution at the moment. If you try to come up with a stable solution, I'm sorry, probably in several months you probably realize it cannot even run some of the latest version. But one thing I would like to recommend is a lot of people mentioned, so what exactly are you going to do? I think a Kubeflow could be a framework that you can try. There are several reasons. First of all, Kubeflow is a very actively develop, which means finding framework, making any change, Kubeflow will try to catch up as soon as possible. Secondly, Kubeflow has a very big community. As far as I know, Kubeflow has a lot of developers actually contributing to that. They try to make an adjustment as soon as possible. So if the upstream framework like TensorFlow make a change, Kubeflow tend to catch up very soon. Yeah, that's I think that's pretty much for today's talk. Another thing I want to mention is the Kubeflow also has several shared API and best practices. They have a common standardized API spec. They have a base job controller interface. And they consolidate all that in one in one repo, but they have different they consolidated those common API spec, common utility functions into one repo, but they have different ways of deploy different framework. Like they have a TF operator, PyTorch operator, and they also have MPI-operators. That's pretty much for today's talk. Any question? Okay. Yeah.
Regarding model serving, what's your recommended technology? Sheldon or others?
Okay, that's that's another interesting topic. If you talk about you're talking about serving models like I mean, of course you have TF serving. That TF serving is one that's coming out of Google as well, but I think they're also falling behind with 2.0.
Falling behind.
Yes, it's
not compatible with 2.0 models.
In 2.0, a lot of things have changed. Remember, in TensorFlow 2.0, first of all, you have eager execution enabled by default. Secondly, so when people in the past when 1.0, 1.x, a lot of the frameworks use TF estimator as a default framework. Now this framework is being phased out. Of course, TensorFlow is still supported TF estimator, but that doesn't mean it's a first-class system anymore, to be honest. So I can only say a lot of things will change pretty soon for TF serving as well. And also in TensorFlow 2.0, another concept is the so-called TF function. TF function essentially is a small subgraph that helps you to optimize. Remember, in 2.0, a static graph has been replaced by eager execution. In eager execution, every step it can run imperatively. But this actually slows down the speed of training dramatically. So one way to improve that is you can define a small function. A small function is essentially a subgraph or a small graph. This graph you can apply, so that gives you the advantage of graph optimization. At the same time, it still gives you the eager execution capability to allow you to do the debug. So with TF function, if you try to let's say you try to write a model, you can come with you can run it in an eager mode, and if you stabilize and decide that say your model is pretty much free, you can convert that into TF function to speed up. So that's another thing that's going to help you. Like I said, a lot of things are in the change in 2.0, but I think that's all good change because, like I mentioned, for model building, you have curves consolidated. You don't need to think about which is the best way to build a model among the 4 different ways of building that. And also with eager execution, that really helps a lot for debugging purposes.
Okay.
Any other questions? Okay. Thanks, everyone for coming here. Have a wonderful day.